Good morning. This is Word Harriman, AE6TY. Today I'd like to spend some time exploring some issues concerned with feed point calculation and maybe a little study in matching losses. Recently, a new user, DJ7BA, asked if there was a way to compute antenna feed point impedances based on measurements made at the rig. This is a frequent question, and the best answer has evolved over the years. I thought I'd take this chance to explore the specifics of his antenna system and take note of some of the peculiarities therein, and review a few lesser-known features of SimSmith. There are at least three reasons why we might want to do this calculation. One, measurement of the feed point impedance is impossible. For example, here's his system. He wants to measure the feed point impedance right here. Well, that turns out to be a difficult thing to do in the absence of the matching section and the feed line, because measuring the impedance at the exact end of a half-wave dipole is pretty difficult. Another reason is that measurement of the feed point impedance might be inconvenient. For example, this may be up 40 or 50 feet in the air. And even a rough approximation is highly useful to examine bandwidths of your matching network and power losses. Here is the basic drawing of his system. It's a half-wave dipole, end-fed, with a quarter-wave resonant transformer. Now notice this is not a ZEP because it's not a quarter-wave matching section. This section from here to here actually resonates back and forth. This is a very high impedance, and if you walk up this point, somewhere in here there's going to be a good match for 50 ohms. Now, this is a resonant transformer transmission line, and this is described in one of the antenna compendium, and I apologize for not knowing which one it is. It's also mentioned in passing in the ARRL antenna handbook. We'll notice also here that because this is end-fed, you need some type of counterpoise, although this is a debatable topic in our hobby. I believe you need a counterpoise, and in this case the counterpoise will at least be this quarter wave section. And if you'll notice here, he doesn't even have a choke here, so the counterpoise for feeding this end fed is actually his entire feed line. Now he mentions that this feed line is largely laying on the ground, and so there's little chance of the common mode stuff getting well back into his rig, which may be why he doesn't have a choke. But I wanted to point that out just in case you tried to replicate any of this stuff. Now, it's important to understand the limitations of what I'm about to show you. I expect that the introduction of the choke may well have a significant impact, but I'm not going to explore that. Now, what happened here is the user built up this system, and he came down here and he made his measurements right here at the rig. And he would like to know this feed point impedance so that he can examine various changes in this circuitry. I want to point this out. If you were to just subtract all this stuff out and believe that it had gone away entirely from the analysis, you would be wrong. Because if you were to delete all this physical coax, and if you could in fact, in theory, measure the impedance right here, you will have subtracted out the effect of any counterpoise or any capacitive or inductive coupling between the now missing feed line and the half-wave dipole. So I want to be a little careful here. This is mathematically correct, but in physical cases, this won't match up exactly because you've actually removed an electrically significant piece of your circuit. So what do we have? Well, here's the circuit that he sent me. And he had a test point in here, but it's basically the top half of the of the resonant transformer and the bottom half of the resonant transformer and its feed line. And he made measurements which tell us about the impedance right here at the input of T3 or the output of the generator. And he would like to know what were the impedances over here at the feed point of the antenna. Now we can get one of those points simply by coming over here and dragging the load around a little bit. And if I work on it, this is pushing a rope, but I can get it fairly close. There's one data point. So we know that our feed point impedance is over here. That's not too surprising since it's an end-fed dipole. Now what we'd like to do, of course, is to compute all of the points over here and see what this trace looks like. And that's what we're going to try to do today. Now, traditionally, the way we did this was we basically tried to back out the impact of these transmission lines. So for example, we knew the impedance here and we just wanted to back out this piece of the feed line and get the impedance here, and then we wanted to back out this piece of the feed line or matching section to get the impedance here. And the way we traditionally backed things out was to simply subtract out the transmission lines. And in order to do that, we needed to first start with the impedance measurements. Now we put the impedance, this is traditional, we put the impedance measurements down here because we're about to run this circuit in reverse. So here's the impedance data that he sent us. And let's take a quick look at it. Here's the impedance that he made, the measurements he made at his rig. And we want to know what happens as we walked back this way. And the way we're going to do that is we're going to simply copy this section of line. We're going to put it over here next to the measurements. Remember, we are working on measurements going this way, so now we're going to start with measurements and work the other way. And we're going to subtract out that effect by simply putting in a minus sign. And now we could plot this point at T4, and we could see that the effect of that feed line was essentially a rotation around the origin. And that's not surprising because the last piece of the feed line, this match got it to 50, so the last piece of the feed line just rotated it. So we can continue on with the process. And now we'll see that we have a mirror image of our original circuit over here with minus signs dumped in. And so we would expect this impedance, let's turn this off for a moment. We'd expect this impedance to go, gets transformed by the feed line, get transformed by the matching section. Here's the feed point. Now we put the feed line back in, the matching section back in, and the feed line. So this, since these are the reverse negative of these, we would expect this trace to look just like this trace. So let's see if that happens. They're both green, so that makes it a little difficult. But you'll see, turn off the load, turn this on. Lo and behold, those two traces look the same. And that means that right here must be the impedance of the feed point. And here's our trace, which is the impedance of the feed point. Now this strikes me as a very odd trace, and I don't even know how to think of this trace because it doesn't look like a normal antenna. These lines coming down through here, those are resistances, parallel or series resistances. And so this looks like as the frequency changes, the resistance changes. And again, this is just an observation. I don't even know the physical reasons for this, but you'll notice that in fact this resistance is decreasing as the frequency goes up. Okay, that's all I'm going to say about that because I don't know how to interpret it. So what we'd like to do is to provide a file which describes this load. So before I do that, I want to save this away for you. And we're going to name this reversed circuit. So now we have that saved away. And we want to use SimSmith's ability to write files to write out this set of impedances. And the easiest way in SimSmith is to use this command, write touchstone S1P files. And that writes out the impedance as seen from the generator. But this circuit doesn't do that. What we really want is to get rid of this. And now we want to write what the generator sees, which is in fact this trace. Now to do that in a way that we recognize, I'm going to go change preferences a little bit here. Well, they're right already. I want the touchstone file to write Z, just basic impedances. And I want the reference to be 1 ohm so that the entries in the data are not scaled by some reference factor, which is the normal case for touchstone. So this is a little unusual, but I'm doing it for readability's purposes. So I'm going to come back here, and now I can just write the S1P file, which again is going to write the impedance as seen by the generator. And I'm going to put it in that folder so that I can share it later. And I usually like to verify that what I did is in fact what I did. So I'm going to use a reference. I'm going to add a reference, which is the data that I just wrote. And it should overlap over here. So if I turn this on and off, you'll see the feed point reference down here. Okay. So we got our feed point impedance data written out, which was the goal of this talk. Now, this approach works really well with certain restrictions. Okay, the first one is that the elements in your circuit are things which you can negate by simply negating something. Like for a resistance, that works fine because you can add a negative resistance, capacitors, inductors, transmission lines, all those things work fine. If, however, you are doing something more complicated, this starts to be a little more difficult. So for example, if one of your circuit elements was described by a manufacturer's scattering parameters, there's no easy way to say just like the negation of the scattering parameters. At least I don't think so. There's other times where this is hard. For example, if you have a Roos block somewhere in your circuit and you have a complicated circuit in here, this all works fine. You could come in here, set all these to be negative, and then you would have to swap these two ports, which again, you can certainly do, but it's cumbersome and it's prone to error. So given those restrictions, some years ago, I went about putting in another capability in SimSmith. So now, those of you who have been using SimSmith for a while have probably run across the idea that SimSmith actually performs 3 different circuit analyses each time it UC1. It computes this direction, which is what we normally think of as Smith chart analysis, from load to generator. But SimSmith also computes two kinds of backwards things, starting with the generator and working this way. One, called the reverse, really just runs this backwards. So starting with some impedance here, it takes this feed line into account, then it takes this stub into account, then it takes this feed line into account, and it computes this. Just like if we had reversed it, but not negated any of the values. The other kind of backward computation SimSmith made is called the inverse, and it starts here and it subtracts out the effect of this, and then it subtracts out the effect of this, and then it subtracts out the effect of this, and delivers it here, which is exactly what we would like to have done. And in fact, what we did do by reversing the circuit and adding in the negative lengths. Okay, so SimSmith does the backward analysis a little differently than the forward analysis. The way it does the backward analysis is based on information left around during the forward analysis. And the way forward analysis works in SimSmith is it starts here, and it computes the ABCD transmission matrix for each of the circuit elements, and then it applies them as a transform going from load to generator. So it computes an ABC matrix for this one, and then it computes it for this one, and it computes it for this one, and it computes it for the S parameter block, and the Rus blocks, and the N blocks, and the F blocks. Everything gets an ABC matrix description. Then, to do backwards things, in the case of inverse, it uses the inverse of this ABCD matrix in order to compute this point. And then it uses the inverse of this ABCD matrix to do this point. And this is all, in case you're interested on the inside, but the reality is, the bottom line is, it doesn't really come in here and say, this is a transmission line, I'm going to assume it's got a negative resistance and move on its merry way. Okay? So it's a general purpose, works with anything, and it doesn't need to know about how to make things negative. It's just using the inverse of the matrices that it's already computed. So let's see how we can go about using this. Well, the first thing we need to do is get our circuit back. So I'm going to load our circuit back, his original. And as I said, it starts on this side with some impedance, and if you don't do anything, the impedance of the generator is assumed to be 50 ohms. But we don't want it to be 50 ohms. We actually want the impedance of the generator during this inverse computation to be specified by the measurements that the user made at this point. And in SimSmith, a hidden feature, it's documented, but it's a little hidden. You can set a special parameter to come from a file. Zgen is the magic parameter, and we're going to say we want to get it from a file. And the file we want to get it from, of course, is the measurements that he made. So now all I've done is I've told it that Zgen, which is used for the inverse computation, comes out of a file, and we could actually plot that. Let's do a plot. And turn off the other traces. Okay, so here we have the measurement data that we saw earlier, and we're using it. We're plotting Zgen, and that's the trace that's going to be used for these backward computations. Now, suppose I want to know, let's take just a quick look. Let's see if we can see the impedance right here, and we can do that by saying on the Smith chart, we want to plot T2.invz. INVZ being the inverse impedance as seen at the point, which would be looking right, seen at the point of T2. And we can see that we expected this to just be a rotating component, and we see here's Zgen, And here's inverse z at t2, which is in fact just a rotation. And we could walk it all the way back, but I'm going to jump right to the end, and I'm going to say, what's the impedance as seen at inverse impedance, looking from L back to the right, and here's what we see over here. And if you remember, we computed it that other way. Let's see what it shows. We'll add a reference, and we used that as the file we had written out previously. And you'll see that the two overlap right over here. So in fact, the old way of using negative values and reversing the circuit delivered exactly the same impedance file as the new way, which is using the inverse computation built into SimSmith. So we see that the inverse calculation is working the same, but it has several added benefits. It works with any circuit elements. You don't need to reverse the circuit or negate values. You don't need to swap ports and roost blocks. It works for basically any circuit. Now, the downside of this approach is that there's no single button way to write out L.invz. No way to write a file which produces this value in the inverse case. But there is a way to write it, and we're going to use another seldom used part of SimSmith, which is the plot write data file. And I'm just going to go do it so you can see how it's done. The first thing we want to do is what's called a legend. And we're going to call the file we're going to write it to is called feedpoint.dat. And we want the legend to say, I'm going to say this because this is a file format that SimSmith knows how to read. And then I want to write some data. So I want to write, I get to specify the format. This is a Java format. So you can go read about Java format or on the web. And then I need to write two data points, one for this format and one for this. And I want to write L.inverse z dot the real part of that. This is a new feature in recent versions of SimSmith that you can just say you can just say .r instead of real. And then I want to do L.invz.x. And now I want to write that file. So here I come and I say, write plot result files. And we want to put it in this directory for you. Oh. And there you have it. And of course, just to be thorough, we'll put this one in as well. And we see that it again overlays all the other mechanisms that we've used to compute the feed point impedance. So there we have it. We have our feed point impedance file computed a couple different ways. One in a kind of intuitive, use SimSmith to do the math kind of thing where we reverse the circuit and negate the component levels. And one using the internals of SimSmith, which is a universal solution. So let's use one of these files and take a look at the circuit operation. And we can do that by simply coming in here. Well, let's get rid of these. We can turn that off. We want to use that feed point impedance file that we had worked with, and we'll put it in there. And now here's the feed point impedances that we computed. Here's our circuit. So we would expect the circuit as seen at T3, or the generator, to be the same as Z-gen, which is the measurements that we made. So here's Z-gen, and here's the load impedance file, or the feed point file, and the circuit. We turn that on over here, and we see, lo and behold, thank goodness, the exactly overlap. Always a good thing to see. So now we have a circuit. And we have this loaded file, and now we can start to ask questions about our circuit, because now we see what is a reasonable model out here for this specific physical feed line with or without chokes, with laying on the ground, of the whole kit and caboodle. One of the fun things to always look at is power. Now, the user, and most users use the generator function, use Z0. I'm not a fan of that under this circumstance, because I want to look at power losses. And to look at power losses, I need to know how much power is going in. And use Z0 will deliver 100 watts in this case, only into a load of 50 ohms. Well, I wanted my rig, or his rig, is probably a little more forgiving than that, and it probably delivers 100 watts into any load reasonably close to an SWR of 1. And the way SimSmith does that best is by using this down here, which is called the transmatch. Now, the transmatch circuit in SimSmith will deliver 100 watts, this argument in here, into any load. And since most of our loads are going to be close to SWR equals 1, it's a reasonable approximation. So I'm going to use Xmatch, so I'm getting 100 watts in. And here we see the generator, and it says right here that it's delivering 100 watts into, which is on the right-hand side, into this. And let's look at what happens at the power in each one of these elements. So if I click on this right here, I can get the power in different ways. So for example, here is the power being dissipated by each one of these elements. So this 23 meter feed line is taking up 4 watts. This shorted stub is taking up 6 watts, and this resonant piece of the quarter wave resonant transmission line transformer is taking 21 watts. So this whole feed mechanism is taking up about a third of all the power being delivered by the transmatch. Now, I want to point out that we're using a simplified transmission line model because this is what my user sent to me. That's pretty lossy stuff. That's like RG58. The default transmission line in SimSmith is pretty close to RG58. It's not, but it's close. He probably uses better transmission lines. And if he went back in here and changed the model of the transmission line, then he would probably get better power. Now, I'm not going to do that, because if I changed the properties of all of this, then I would change the computation of the load file, and we'd be around the loop again, and I don't see any reason to do that for you. So that's the use of the computed feed point file to do a little bit of power analysis here. And now, if I had time and I was interested, I would go and play perhaps a little bit with this matching network to see if I could get this trace to be a little more in the middle. So there's a bunch of different things I can do now, because I have this load file, to see how my matching circuit and my feed line affect the performance of my antenna system. In wrapping up, I showed you a couple different ways you can compute the feed point impedance file. and why you might want to do this. I hope that this video has helped those specifically interested in feed point computations. But I also hope that anybody who lasted this long got to see a little bit more of what SimSmith has built into it and some of the lesser known capabilities that can be used to analyze your circuits. This is Word Harriman, AE6TY, saying thanks for watching and thanks for using SimSmith.